Hello dear students, welcome to the channel and very welcome to this playlist in which we are discussing about the second chapter of instrumentation and sensors. And up till now we have seen different type of instruments, different type of sensors. In previous since last few previous classes we were discussing about the uncertainties in measurement and the error in measurement. So we have discussed about its types, we have discussed about the methods to minimalize the error, and we have discussed about how we will be detecting the error. We have discussed about the systematic errors, environmental errors and random errors in detail, and now we are going to discuss, and we have also discussed about the methods to solve these errors, the methods to overcome such errors. And in previous class only we have discussed about the methods to overcome the random errors. So if you want to learn more about the random errors and how to get rid of it, check out the previous video. And um, also if you want to learn about the second chapter of IS, check out the playlist. The link will be flashing on the top right hand side corner of your screen in the I button, so you can click on it and check out the videos. And today we are going to discuss about the standard error of the mean, and we are going to combine what we have learned throughout all these measurement or uncertainty techniques, and trying to find the cumulative error. Okay, so now let's first discuss the remaining portion from previous class. So this video is going to be the continuation video from previous class. So last time we have discussed about the standard Gaussian errors and standard Gaussian means, and today we are going to continue that by discussing standard error of mean. So all this analysis that we have done so far has examined the way in which measurement with the random error are distributed about the mean values. But we have already observed that some errors remain between the mean value of a set of measurement and the true value. Like averaging a number of measurement, it will only yield the true value if the number of the measurement is infinite. So if several subsets are taken from an infinite data population, then by the central limit theorem, the means of that subset will be distributed about the mean of the infinite data set. And the error between mean of the finite data set and the true measurement value is defined as the standard error of the mean, which is indicated as alpha. And this alpha or standard error of the mean is calculated by sigma divided by root n. Okay, and this alpha tends to towards 0 as the number of the measurement in the data set expands towards the infinity, right? And by the way, this n is the number of measurements in the data set. Delta is the standard deviation that we learned from previous class. So the measurement value obtained from a set of n measurements, let's say going from x1 to x2 up to xn, can be then expressed by this equation: x is equals to x mean plus or minus alpha. Okay, then they have shown us an example in which they took n is equals to 23, sigma equal to 1.88, alpha equal to 0.39. Okay, and then they have said that this length can be expressed as 406.5 plus or minus 0.4, which indicates the value of x mean is 40.5 and the value of alpha is 0.4, right, which was previously 0.3439, but we rounded it off to 0.4, which means 68% confidence limit. However, it is more usual to express measurement with 95% of confidence limit. So what will you do? You will take the twice of whatever sigma you have, right, to extend the boundaries. So when you take the twice of the sigma, see what is the value of sigma, 1.88, so the twice of that will be 3.76. And as you are taking alpha twice of the sigma, or sigma into sigma, then you also have to take twice of alpha, alpha into alpha. That would be 0.78, right? 0.39 into 0.39, 0.78. Sorry, 0.39 plus 0.39, 0.78. So the length can be expressed as for 95% confidence limit, the length can be expressed as 406.5 plus or minus 0.8. Okay, so now we have extended our boundary. But in some situation, what happens, when instruments are subject to random errors, it is not practical to take repeated measurements and find average value easily. Plus, the average process will become invalid if the measured quantity does not remain in a constant value. So, as is usually the case when process variable are being measured, thus if only one measurement can be made, some means of estimating the likely magnitude of the error in it is required. And whatever the normal approach we were pushing till now was used to calculate the error with 95% confidence limit. So to calculate the value of the deviation d, like which is around 95% of the area under the probability curve, lies within the plus or minus d limit, right? And this limit corresponds to the deviation of plus or minus 1.96 sigma, right? We took twice of it. So thus it will become necessary to maintain the measured quantity at a constant value while a number of measurements are taken in order to create a reference measurement set from which this sigma can be calculated. And subsequently, the maximum likely deviation in a single measurement can be expressed using this equation, plus or minus 1.96 into sigma. But this is only expressed the maximum deviation of measurement from calculated means of the reference measurement set, which is not the true value as observed earlier. So the calculated value for the standard error of the mean has to be added to likely maximum deviation value, and thus the maximum likely error in a single measurement will be given using this equation, plus or minus 1.96 sigma plus alpha. Then they mentioned an example. We are not going to see that, we are running out of time here. Then we have the distribution of manufacturing tolerance, which says many aspects of manufacturing process are subject to random variation, which are caused by factors that are similar to those that cause random errors in measurement. And in most of the cases, these random variation in manufacturing are known as tolerance, which fits a Gaussian distribution. And previous analysis of random measurement errors says that it can be applied to analyze the distribution of these variation in manufacturing parameters. Okay. Then there is one more example. We are not going to discuss the examples. Then goodness of a fit to a Gaussian distribution, that we are going to see, and it is very important because all of the analysis of the random deviation which are presented so far only applies when data begin the analysis. The data being analyzed belongs to Gaussian distribution, but the degree to which the set of data fits a Gaussian distribution should always be tested before any analysis, right? So this test can be carried out in one of the three ways. First one is a simple test, which is a simple way to test for a Gaussian distribution of a data. If it is to plot a histogram and look for a bell shape of the form, which we saw earlier in the previous class, and then deciding whether or not the histogram confirms a Gaussian distribution is a matter of judgment. So for a Gaussian distribution, there must always be a proximate system, right? Proximate symmetry about the line through the center of the histogram. So the highest point of the histogram must always coincide with the line of the symmetry, and the histogram must get progressively smaller either side of the point. But because the histogram can only be drawn with the finite set of measurements, some deviation from perfect shape of the histogram, as described in that shape from previous class, is to be expected even if the data really is Gaussian. Then next way or second way is using a normal probability plot. A normal probability plot provides dividing the data values into number of ranges and then plotting the cumulative probability of the sum data frequencies against the data values on special graph paper. And this line should be straight line if the data distribution is Gaussian. But careful judgment is required because only a finite number of data values can be used, right? Only finite number of data values can be used, and therefore the line drawn will not be entirely straight even if the distribution is Gaussian. There will be considerable experience, right, which will be required to judge whether the line is straight enough to indicate Gaussian distribution or not. And to understand that, they have provided an example of measurement set C using the same five ranges as used to draw the histogram. They have driven this table C. We took 101 401.5 to 401.5 to 403.5, then 403.5 to 405.5, and so on. They took five ranges. Then they divided the number of data items in per based on the range. So there was only one data item in first range. We will call it R1, R2, R3, R4 and I5. So one data item in R1, 5 in R2, 11 in R3, 5 in R4 and 1 in R5. Right? The number will only tell that this is okay, this is something that is making the Gaussian curve. Then when you take the cumulative number of the data items, first we have 5, then first we had 1 only, then 1 plus 5 we will get 6, then 6 plus 11 what we will get, 17, then 17 plus 5 we will get 22, 22 plus 1 we will get 23, and then cumulative number of the data item as percentage, right? So total there are 23 items, and when you take only one item then it would be 4.3% of the 23. Similarly, 6 items would be 26.1% of 23. 17 items would be 73.9%, and 22 items will be 95.7%. So the normal probability plot drawn from the above table will look something like this. See. Right? 5. See. 22. This is the percentage going from here to here. See. Close to 5, 4.3. Then we have 26.1. This is 26.1. Then we have 73.9. Right? Here we have 73.9. 95. So this will be 95. And then here we go close to 100. So this is sufficiently straight to indicate that data is measured, measurements that C is the Gaussian data. And the third technique is the chi-square technique. And this is a very popular technique that you must have seen in so many other places as well. In this technique, a further test that can be applied, which would be based on the chi-square distribution. Okay. And if you want me to make a video on chi-square, this is not the part of our syllabus, so we are not covering that. But if you want me to make a video on chi-square technique, please mention that as well. I am pretty sure many of you would have heard about it or have learned about chi-square technique, as it is very popular technique. So if you want me to make a video on it, please mention that in the comment section, so I will make a video on it. Then we see the rogue data points. So in a set of measurement subject to random error, measurement will with a very large error sometimes occurs at a random and unpredictable times. So where the magnitude of this error is much large and even larger than it could reasonably be attributed to the expected random variations in measurement value only. So sources of such abnormal error include sudden transient voltage surge on the main power supply and incorrect recording of the data. So it is accepted practice in such cases to discard these rogue measurements, and threshold level of a plus or minus 3 sigma deviation is often used to determine what should be discarded. It's extremely rare for measurement error to exceed plus or minus 3 sigma limit when only normal random effects are affecting the measurement or measured value, right? Then we have a special case when the number of measurements are very small. So number of measurement are very small, particularly small, and statistical analysis of the distribution of error value is required. The problem can arise when using the standard Gaussian tables in the terms of z as defined in that equation that we saw earlier, 3.16. Let me take you there towards equation 3.16. Here you go. Standard Gaussian table that we learn based on this equation. And let's see what does it has to say. Because the mean of the only small number of the measurement may deviate significantly from the true measurement, right? So in response to this, an alternative distribution function which is known as the student t distribution can be used, which gives a more accurate prediction of the error distribution, right? When the number of the small samples we take, we can understand that. The next is the aggregation of the measurement system errors, which we saw up till now, right? Because in practical system, whenever you are operating on a practical system, the error will not only be a systematic error, or it will not only be an environmental error, or neither will it be an random error, right? You will get aggregation of all three. You will get the combined error, right? So these must be aggregated in the correct way in order to obtain a prediction of the total likely error in output reading from the measurement system. And for that, we use two different aggregation forms. First is a single measurement component, which may have both systematic and random errors. And secondly, the measurement system may consist of several measurement components that each have separate errors. Okay, so let's see the first one, the combined effect of the systematic and random errors. So if a measurement is affected by I beg your pardon for that. So if a measurement is affected by both systematic and random errors that are quantified as plus or minus x and plus or minus y, some means of expressing the combined effect of both types of errors is needed. And one way of expressing the combined error would be sum of the two separate components of error, which means to say that the total possible error, however, a more usual course of action is to express a likely maximum error will be E is equals to under root plus or minus E is equals to under root x square plus y square, right? And it is visible that this is the best expression for the error statistically, because it takes account of the reasonable assumption that the systematic and random errors are independent, right? And so are unlikely to both be their maximum or minimum value at the same time. Then we have the aggregation of the errors from separate measurement system. So a measurement system often consists of several separate components, each of which is subject to errors, and therefore what remains to be investigated is how the error associated with each measurement system component combined together, so that all that a total error calculation can be made for the complete measurement system. All four mathematical operations, addition, subtraction, multiplication, division, may be performed on a measurement device from different instrument or transducers in the measurement system, and appropriate techniques for various situations that arise are covered. Okay, and let's see them each and every situation one by one. First is the error in the sum. So what does it has to tell us? It says if the two outputs y and z of the z separate measurement system components are to be added together, we can write the sum s is equals to y plus z. If the maximum error in y and z are plus or minus ay and plus or minus bz respectively, we can express the maximum and minimum possible values of s using this equation. S max is equals to y plus ay plus z plus bz. And for minimum value, we will take y minus ay plus z minus bz. Or otherwise, you can also write s is equals to y plus z plus or minus ay plus bz. Right? It will give you the maximum and minimum value altogether. Now this relationship for s is not convenient. Why? Because this form of the error term cannot be expressed as the fraction or percentage of the calculated value for s. But fortunately, statistical analysis can be applied, and then the expression can be altered. How and such that the most problems will vanish, right? And for that, we will get a different quantity which will be called E, or the absolute error. And the formula for that E will be given as this: E is equals to under root a y square plus b z z square. Okay, thus the y will the value of s will be y plus z plus or minus this E. Okay, and if you want me to write it down alternatively, you can write it this way: y plus z in bracket 1 plus or minus f, where f will be E divided by y plus z. Right? So it should be noted that both of these equations are only valid provided that the measurements are uncorrelated, which means each measurement is entirely independent of the other measurement. Now let's learn this in a better way with the help of an example that says a circuit requirement for resistance is 550 ohm. It's satisfied by connecting together two resistors of nominal values 220 ohm and 330 ohm in series. So if each resistor has a tolerance of plus or minus 2%, the error in the sum calculated according to the equations which we saw earlier is given using this formula. So we have to find the value of S. Now you already have the formula. You know the value of the errors: 550, 330, 220 ohms, and you know the value of E as well, right? Plus or minus 2%. Sorry, you know the value of this small e, right? Or you can say your A and B plus or minus 2%. So you can find the value of E. Based on value of E, you can find the value of F, because F will be E divided by Y plus Z. So divide this E by Y plus Z, you will get 0.0144, right? And thus the resistance S can be expressed with the value of 550 ohm, which was the value, plus 7 point plus 7.93, the value of F ohm, right? And thus you will be getting value of I is equals to 550 ohm plus or minus 1.44%. Now let's quickly see error in the difference. So if the two outputs y and z of separate measurement systems are to be subtracted from one another, and then possible errors are plus or minus ay and plus or minus bz, then the difference s can be expressed with the equation s is equals to y minus z plus or minus e, s is equals to y minus z 1 plus or minus f, where E is calculated with the equation which we saw earlier, under root a plus a ay square plus bz square, and f will be E divided by y minus z. And for that also they have given an example. Says a fluid rate is calculated from the difference in pressure and measured on both sides of an orifice plate. If pressure measurement are 10 bar, 9.5 bar, and the error in the pressure measuring instrument is specified as plus or minus 1%, then we have to find the value of E and F. So again, value of E will be, because it is plus or minus 0.1%, so 0.001 into what is the pressure, 10 bar, whole square, plus again 0.001, what is the pressure, 9.5 bar. Take the square of both of them and take the square root, you will get the value of E is equal to 0.0138. Now to find the value of F, divide this E by sum of y plus z. In this case, difference of y plus z, right? So 0.0138 divided by 10 minus 9.5, so you will get 0.5, and the f will be, when you take the division of both these terms, the f value of f will be 0.0276. And this example illustrates very poignantly that the relatively large error that can be arise when the calculations are made based on difference between two measurements, right? Now let's see the error in the product or the multiplication. So if the output y and z of two measurement system component are multiplied together, the product can be written as p is equals to y into z. And if the possible error in the y is plus or minus ay and in z we have plus or minus bz again, then the maximum minimum value possible in the p can be written using this formula. P max will be y plus ay into z plus bz. So you will be left with yz plus ayz plus byz plus aybz or abyz, and p minimum will be y minus ay into z minus bz. So you will be left with yz minus ayz minus byz plus abyz. So for typical measurement system in which component of this output error of up to 1 or 2% in the magnitude, both a and b are very much less than the number of the magnitude in these terms in aybz, and they are negligible compared to other terms. And because of that we have p max and p min. So thus the maximum error in the product p is plus or minus a plus b, while the while this expression or this expresses the maximum possible error in p, which tends to overestimate the likely maximum error, since it is very unlikely that the error in the y and z will both be at the maximum or minimum value at the same time. So a statistically better estimate of the likely maximum error E in the product P provides that the measurements are uncorrelated. So E will be under root a square plus b square. Simple as that. And note that in the case of multiplicative errors, E is calculated in terms of fractional error in the y and z, right? As opposed to the absolute error, the value used in the calculating are additive errors. They have also given example, but I think from addition and subtraction examples are very clear and simple. Let's see the error in quotation. So if the output measurement y of one system component with the possible error plus or minus ay is divided by the output measurement z of another system component with possible error plus or minus bz, then the maximum and minimum possible value for the quotient can be written using this formula. Q max is equals to y plus ay divided by z minus bz, and you will get yz plus ayz plus byz plus aybz divided by z square minus b square into z square. This will be the final Q max, and the final Q min will be y minus ay z plus bz. So again you will take y minus ay, z minus bz, and z plus bz and z minus bz. So you are multiplying the whole term with z minus bz this time. So you will get this form as q min. Now for a less or equal to 1 and b less or which means a, if the value of a is too less compared to 1 or too small compared to 1 and value of b is too small compared to 1, then these terms in ab and b square are negligible compared with the other terms, and as they are negligible we can simply neglect them. So what you will be left with in the qmax, you will be left with yz into a plus b plus 1 divided by z square, and q min you will be left with yz into 1 minus a minus b divided by z square, which means the value of q will be y divided by z plus or minus y divided by z a plus b. Simple. So the maximum error in the quotient will be plus or minus a plus b, but using the same argument made above earlier for a product of the measurement, a statistically better estimate of likely maximum error in the quotation q, provided that the measurements are uncorrelated. One more time. Now let's see the total error when combine multiple measurements, which is the final case we are going to cover. So when we combine several measurements that are together in a way that involves more than one type of arithmetic operation. For example, a density of rectangular sided solid block of a material can be calculated for measurement of its mass divided by the product of the measurement of its length, height and width. So the error involved in each stage of the arithmetic and cumulative, and so the total measurement error can be calculated by adding together the two error values associated with the two multiplication stages which are involved in calculating the volume and then calculating the error in the final arithmetic operation when the mass is divided by the volume. So they have explained this with the help of example here. Let's see the example and end this class. So a rectangular sided block has edge of length a, b and c and its mass is m. If the value and the possible error in the quantities a, b and c and m are shown here, then we have to calculate the value of density and the possible error in this value. So the value of a is 100 mm plus or minus 1%. In b we have 200 mm plus or minus 1%. C we have 300 mm plus or minus 1%, and mass is 20 kg plus or minus 0.5%. So first we have to find the value of AB, right? So it will be 0.02 meter square plus or minus 2%. 1 plus 1 will be 2. 100, 200 percentage wise 0.02 meter square plus or minus 2%, and possible error will be 1 plus 1 equal to 2%. Again value of AB into C. So 0.02 into 3, you will be left with 0.006 meter cube, because this time we are taking third variable here, and possible error that also has the 1%. 2 plus 1 will be 3% of error. Now we have the mass, so this time we have to take the division, right? So this time we take mass divided by volume to find the density. So we will get what is the mass, 20 kg. And also if you are confused why did we took 0.02, this was in millimeters, okay? Some of you may have confusions related to that. So this was in millimeters, so we converted into the meter, and that is why we are having 0.02 and 0.06. So mass divided by the volume, 20 divided by 0.06 will be 3330 kg per meters cube. And what was the error? 0.5. So we already had error of 3%. 3% plus 0.5%, we will have 3.5% possible error, right? So that was the total error when combining the multiple measurements. So we will keep today's class till here only. In the next class we will be discussing new topic related to this chapter only. If you have any doubts, queries, questions related to today's class or any other class, please feel free to mention them in the comment section below. I will try to answer them as soon as possible. If you have any feedback related to the channel, these videos, these playlists, or anything, mention that in the comment section below as well. I am waiting for your feedbacks. And also, if you have any suggestions or recommendations for me to make a video on something, mention that as well. I will try to make a video on that as well if that thing falls into my expertise. So we will keep today's class till here. Thank you very much for listening. Mention your doubts in the comment, and see you next class. Goodbye for now.